Hello, good morning. Myself, Dr. Lakshmi Devi, Professor, Department of ECE, St. Peter's Engineering College. In today's topic, electronic devices and circuits, clippers and clampers. This is the first unit of JNTU H affiliated colleges under the subject of electronic devices and circuits. First unit, clippers and clampers. As an application of diodes, we are having this particular topic of clippers and clampers. So let us see here uh, what are these clippers and clampers, in what way we are making use of this, and what's meant by clipper and what's meant by clamper. These are all the things we would like to cover in today's class. Clipper circuit. Just I told you already, these are the applications of clippers, applications of diode. A clipper circuit prevents the output waveform from exceeding the certain level, and at the same time it does not distort the remaining part of the waveform. So basically, it's having its own applications for the clippers as well as clampers. Regarding to that particular point, so we are actually using these clippers as a main applications of the diodes. Just here, it's a diode symbol. The direction of current flow we are showing here, the direction of current flow as I, and this is the direction of current flow. This is the diode symbol, and here we have a resistor. So a clipper circuit with the combination of this diode and resistors in general we can use for clippers. So here the waveform just having certain deviations from its original shape, but there is no chance to have other parts of the waveform to be changed in the clippers output. See here, in what way we can show as a clipper circuit means, suppose this is an input. It's a given input of sinusoidal, and this is the clipper circuit. Just as an application of diodes, first we can show the rectifiers. So which converts AC into the pulsated DC. In general, we define it as actually the rectifier. Under this rectifiers, the first one is a half wave rectifier. So here we are specifying a clipper also acts as a half wave rectifier. How it is means, now this is actually the input waveform, which is sinusoidal input waveform, which is having a time period of 0 to t and a maximum voltage of, we are showing here the Vm, that's the maximum peak voltage is Vm. So this is an input voltage, that's the reason we are representing on y-axis as a Vin, and this is an x-axis as a time. It's an input waveform which is given to the clipper circuit. So with the action of the clipper, here we are having only positive half cycles at its output, but there is no any negative half cycle. Negative half cycle totally clipped off and only positive half cycle gets repeated here. This is same as half wave rectified output. That's the reason we are showing this clipper circuit as a half wave rectifier. And output is actually showing here on y-axis as well as same time period on x-axis. The maximum voltage, there is no any deviation compared to the input. Output also have the same maximum voltage, but certain portion of the input it's totally clipped off. It's totally removed. That's the reason here negative half cycle it's removed in this particular clipper circuit, which is same as half wave rectifier. Half of the wave is repeated at its output compared to the input. That's the reason it's called half wave. Rectifier means without having the full waveform, here half of the waveform is repeated, and rectifier, it's an actually converting of AC to pulsated DC. This is not exactly DC, still we are going to have at its output some filters in the half wave rectifiers that we'll see in the rectifiers cases, but here we are observing the clipper functionality with the use of diodes. Coming to the next, half wave rectifier circuit diagram, just if you observe, this is sinusoidal input we have given, and this one is actually the diode, and here a load is connected as a resistor connected as a load. Now input is given a sinusoidal waveform as an input, and once we have given sinusoidal input, the output of this one we have only half of the waveform. What happened actually, the functionality of the diode. Whenever this terminal is called anode and this terminal is called cathode. Whenever the anode terminal is having higher potential compared to the cathode potential, then the functionality of the diode in forward bias. If it is in forward bias, it acts as a closed switch. That is, the resistance offered by that particular diode in practical cases, it's very low. The same thing, if the diode is, if you consider it's an ideal diode, the resistance offered by the diode in its forward bias is a 0. But there is no any ideal components are available. That's the reason we'll consider this is a practical diode. So the resistance offered by this, each and every component having its own internal resistance. That's the reason whenever anode voltage is greater than the cathode voltage, diode will turn up into on condition. That we'll call it as actually diode is in forward bias. If it is in forward bias, it acts as a switch. That is a closed switch. If it is in forward bias, it acts as a closed switch. If it is a closed switch means it allows whatever the input we are giving, it appears at its output. It's a closed switch means it appears as same at its output. That's why the positive half cycle, during this positive half cycle, similar output we are having like this. Coming to the negative. Negative in the sense, this after crossing the 0, the input voltage, the next leftover part of half of the cycle, that's a negative half cycle, is a negative. That is, whenever the anode is negative, if the anode is negative means with respect to the anode, the cathode becomes the positive. If the cathode becomes positive, then automatically this diode becomes reverse biased. If it is reverse biased means it appears to be open circuit. Whenever the diode open circuited, then the output here output appears to be 0. That's the reason here this yellow line indicates output appears to be 0. So there is no question of any output appears whenever the diode is in reverse bias. So in this way, whenever the next half cycle starts here, the same operation gets continued. The next positive half cycle repeats here and then negative half cycle appears to be 0. So this is an actually operation of half wave rectifier as a clipper here for minimizing of or clipping of a negative half cycle. We are using that particular half wave rectifier. See, basically these clipper circuits are two types. One is positive clipper circuit and the one is negative clipper circuit. So the name itself gives a positive clipper. It clips actually the positive half cycle, and negative clippers means it clips in the negative half cycle. Let us see in depth of this positive and negative clippers. So clipper circuits, again here it's divided into series clipper circuits and parallel clipper circuits. This is another category of clippers based on the connection of the diode. Here we are considering whether it may be series or parallel. If it is a series clipper circuit means load is connected in series with the diode. In series with the diode. A parallel clipper circuit means diode is connected in parallel with the load. Here it's an actually series limiting resistor only we are showing but not a load. So diode is connected in parallel with the load is an actually parallel clipper circuit. Diode is connected in series with the load, we'll call it as series clipper circuit. These are the simple diagrams for understanding sake here given. Input voltage is Vin and this diode RL is the load resistor. If these two are in series, it's called series clipper. If load is diode is connected in parallel with the load, then it's called parallel clipper circuit. This R is meant acts as and actually the series limiting resistor. Okay, these are the two different types of clipper circuits. Now let us see here. First, we'll go for the parallel clipper circuits. Then we'll see series clipper circuits. In the parallel clipper circuits, here load is connected as RL parallel to the diode. Now this is an actually input as a sinusoidal input we are giving as an input to this parallel clipper circuit. During this positive half cycle, in what way the functionality of the diode? During negative half cycle, what happens to the diode? Just we can observe and then we can plot the output waveform. Let us see during positive half cycle. So again, just if you observe the positive half cycle, anode becomes positive and cathode becomes negative. So whenever the anode is higher potential compared to the cathode, then diode is in forward bias. If the diode is in forward bias, it acts as a closed switch. If it acts as a closed switch, then whatever here, in what way we have an actually the output. Just see this particular excluding the drop across the resistor, the remaining here output appears to be in what way we have. See, whenever this one is short circuited based on the positive half cycle, whenever this one is short circuited, this is allowing current like this. Whenever it is allowing current, the drop across the diode is very negligible, because whenever the diode is in forward biased, the resistance offered by a diode is very less. So the drop across the diode is also very less. That is, if it is ideal diode, means the drop across the diode seems to be zero totally. That's why whenever during positive half cycle, diode is in forward biased. If it is in forward biased, it acts as a closed switch. If it is in closed switch, then it offers output voltage is zero. So zero output voltage. Then coming to this negative half cycle. Whenever input voltage enters into the negative half cycle, anode of this diode becomes a negative and cathode with it becomes positive. Because of that, so this is actually changes the diagram. Because of that, negative half cycle, diode open circuited. If the diode is open circuited, whatever the input voltage that appears at its output, that's why negative half cycle repeats in the last circuit. Coming to this parallel clipper circuit only, but if the diode reverses, in what way it functions, just see in this case. As compared to the last diagram, here we are observing a negative clipper. That is, just see, this one is actually the diode is reversing as compared to the last one, and same input voltage is given. Whenever the positive voltage, the positive half cycle of the input is applied to the circuit, during this positive half cycle, cathode of the diode is positive as compared to the anode of the diode. That means whenever the cathode potential is lesser than the anode potential, the diode acts as open circuited. If the diode is open circuited, sorry, the diode is reverse biased, then it acts as a open circuit. If it is open circuited, then output voltage is same as input voltage. That's the reason same positive half cycle repeated here. Same positive half cycle repeated. Okay, coming to the negative half cycle, whenever it is a negative means cathode becomes negative. With respect to the cathode, the anode is positive. So whenever the anode is positive with respect to the cathode, then the diode becomes forward biased. If the diode becomes forward biased, it acts as a closed switch. If it is a closed switch means the drop across the diode is negligible. In case of ideal, drop across diode is negligible in the sense zero. So in general, if it is ideal case means the drop across the diode we are going to observe, this is a zero. Okay, it's the same as actually half wave rectifier. But if the diode is not an ideal case of diode, then definitely each and every practical diode have its own internal resistance. Based on its internal resistance, it's having some drop across the diode. Whenever it is in actually if in the negative half cycle, this diode acts as a closed switch. That closed switch have some resistance. Because of that resistance, it's having some drop across the diode. That voltage we are showing here, this is actually the drop across the diode during negative half cycle. Okay, these are the negative clipper as well as the first one we have already observed the positive clipper. The next, so this is a clipper circuit. By applying some positive biasing voltages, how it acts as an actually how it clips a particular portion of the input waveform at its output. Just see here, clipper circuit with biasing voltages. Biasing voltages mean based on the biasing voltage, it's having changes in its clipping portion at its output of the waveform as compared to its input. Now let us see here input voltage. Let input voltage as well as same as sinusoidal voltage only. The maximum voltage as Vm and time period of T. The sinusoidal input voltage we have given for this clipper circuit with the biasing. So here we have given biasing voltage, that is a DC voltage in series with this particular diode. that is positive supply of the positive terminal of the supply is given to the cathode, and negative supply is given to the actually the input source. Okay, input alternating current source, alternating voltage source. So now let us see here in what way the functionality of this one. Let us observe this particular voltage source of DC having 5 volts, 5 volts of fixed voltage, and a maximum voltage in this case let us consider at 12 volts. That is Vm of AC voltage we are getting maximum of 12 volts, and here the DC biased voltage we have given as 5 volts. In this case, how the functionality of the diode? Just you can observe, whenever input is actually rising from 0 to 12 volts, at particular point it can crosses the 5 volts. That means until to come to the actually the 5 volts of this particular input voltage, this diode is in reverse bias only. What's the reason? Suppose let us see, if the diode is less than 5 volts, if the diode is sorry input voltage is less than 5 volts, anode of the anode of this particular diode is less than 5 volts, but cathode is already connected to the fixed DC voltage of 5 volts. Because of that, whenever the anode voltage is lesser than the cathode voltage, the diode is reverse bias. If it is in reverse bias, it acts as open switch. If it is in open switch, if it is an open switch, the output voltage here in what way it appears? Let us see in this next slide. Okay, if it is an open, it acts as a open switch means this is actually the circuit stays at the time. That means whenever the input voltage crosses, less than the 5 volts, this particular diode acts as open switch. Okay, if it is open switch, this is actually the circuit diagram. Whenever the Vin is less than 5 volts. If the Vin is less than 5 volts, what's an actually the output? Here, if it is open in the sense, it maintains the constant output voltage of 5 volts. So, whenever you'll go for crossing the input voltage greater than this 5 volts. If it is greater than this 5 volts means anode of the diode connected to higher voltage compared to the cathode of the diode. Whenever anode voltage is greater than the cathode voltage, diode short circuited. Diode, that means diode becomes forward biased and it acts as a closed switch. It acts as a closed switch means then output voltage is actually showing, let us see here. Okay, it acts as a closed switch, and after crossing this one, that means after crossing this particular voltage of in this waveform, if it is input voltage is lesser than 5 volts, again the diode is in open circuit. So it's the same way, whenever the diode is in open circuit, it repeats the input waveform. Whenever the diode is in a forward bias, it actually maintains the constant output voltage of 5 volts. So based on the diode condition and based on the biasing voltage here we have given, here we have clipping portion of the clipping portion of its input. That is, whenever the diode is in short circuit and whenever the diode is in open circuit, when if the input voltage is less than 5 volts, this particular diode is in open circuit. That is, diode is acts as a open switch. Open switch, if it is open switch means the output followed by input. That's why we have the same. Whenever input voltage is greater than 5 volts, greater than 5 volts means anode potential is greater than cathode potential, then this diode becomes forward biased. If it is forward biased means it acts as a closed switch. If it acts as a closed switch, whatever the output voltage here it's showing, it appears to be, voltage biasing voltage, it's showing the same 5 volts as its output. As its output. After crossing this in the positive half cycle less than this 5 volts, then automatically this diode becomes reverse biased. If the diode becomes reverse biased, it acts as an open switch. If it is open switch, output is followed by input. That is, output is a replica of its input. That's why output waveform is same as input waveform. So this portion only clipping here based on the supply, based on biasing voltage here. This is an actually a clipper circuit with the biasing voltage in its positive half cycle. Okay, if the diode is ideal case, then we have this type of a flat waveform with the 5 volts which is a biasing voltage supply here, a DC voltage. That's the reason here showing 5 volts. Suppose if it is not ideal, then in what way we have? Let us imagine if it is not ideal means it's also having some internal resistance. Based on its internal resistance, if the diode is in forward biased, if the diode is in forward bias means during this particular period here to here, if the diode is in forward biased, it's having some drop across this. That drop means at around 0.7 volts. To the maximum extent drop across the diode. If the diode is in forward biased, drop across the diode is 0.7 volts. So we can consider that zero point 0.7 volts here as an extra appears like this as compared to the lost waveform. That is V voltage source of V as a 5 volts plus 0.7. So 5.7 volts, it maintains output voltage as a constant whenever the diode is in reverse biased, where it's showing actually open switch. Okay, whenever the diode is in Vn is Vn is greater than that 5 volts, then it acts as an actually closed switch. In its forward bias, actually the drop across the diode is zero point 0.7 volts. Totally, this is an actually the waveform as compared to the last stage of ideal and the practical diodes. This the only change appears. Instead of 5 volts, it's showing 5.7 volts as a constant voltage under this particular period of V in is greater than 5 volts, and here whenever it is crossing this particular point, then automatically diode becomes open circuit. If it is open circuit, this output is same as input. So this is an actually the clipper circuit with the biasing. Let us see the next step. A similar way we can observe here a clipper circuit with a negative biasing also. The last case we observed a positive biasing, that is positive terminal of the voltage source we have given to the anode, cathode, and here we are observing a different phenomena of clipping the negative half cycle by applying a negative bias voltage. How it is? Let us see here. The same circuit diagram, but here the orientation of the diode is also changed, and negative terminal of the supply we have connected to the anode and positive supply we have connected to the input voltage source. This is as usual input voltage as sinusoidal signal, and whenever here input voltage is forward bias, input voltage is positive half cycle, then during that particular period, so if the input voltage is actually positive half cycle means cathode of the diode is positive compared to the anode of the diode. Cathode of the diode is positive and anode of the diode is connected to the negative. During that particular period, diode is in open circuit. If the diode is in open circuit, this output voltage followed by input, that is the output waveform is the same as input waveform. Because of that, the output voltage is here it's the same as input waveform. So whenever, because here it's a negative supply we have connected to its anode, that's the reason whenever the input voltage is actually crosses this negative voltage source, this voltage of this voltage source that is negative, then cathode of this diode becomes lesser potential compared to anode of the diode. That is, whenever the cathode of the diode is lesser than, that is cathode of the diode is lesser than anode of the diode, then the diode becomes forward biased. If the diode becomes forward biased, it acts as a closed switch. If it acts as a closed switch, whatever the voltage source we have given here, whatever the voltage source we have given, that appears at its output. This is output. That is a negative voltage of whatever the voltage that appears at its output as a constant. So after crossing this particular voltage of input waveform, then again input voltage is greater than, that is input voltage is greater than this negative supply connected to its anode. That becomes cathode voltage is a higher potential as compared to the anode potential. At that time, the diode becomes again reverse biased. If the diode becomes again reverse biased, then input followed by output followed by input. The same waveform here it repeats. So here we can observe based on different biasing voltages, actually how we are observing the clipping portion of its output waveforms. So after completion of these clippers, a student should be in a position to identify how we are going to generate the different shapes of waveforms pertaining to suitable for a different applications point of view. Okay, this is an actually input waveform, and with this particular biasing conditions we have observed this is an output waveform. The next, so in this case a clipper circuit with the biasing voltages, but two different biasing voltages with the parallel connection of two diodes, how it works and how we'll be having the output waveform. First you have to analyze, then I'll show you the output waveform. Now let us see, diode 1 is biased with a particular voltage, that we'll call it as actually a positive terminal of the voltage source is connected to the cathode of the diode D1, and in case of second diode D2 is biased with the voltage of V2, but in this case negative terminal of the voltage source is connected to the anode of the diode D2. Okay, these two diodes are connected in parallel with the series limiting resistor of R and input voltage source V in a sinusoidal input voltage source. Now let us observe the functionality of this circuit diagram. Now first, whenever the input voltage raising from 0 to the maximum of Vm, what happens actually the condition of this D1 and D2s. Now whenever the input voltage is varying from 0 to Vm, see this first D1 stays. D1 input voltage diode is connected to the input voltage source. So this V1 positive terminal is connected to the cathode. So if you have imagined, if the V1 is 5 volts and Vm is equals to 12 volts, like Vm is 5 volts. So whenever input waveform crosses this 5 volts, then only anode of the diode D1 becomes higher potential as compared to the cathode of the diode. Until to reach that point, this particular diode is in reverse bias. That means whenever the anode potential is greater than the cathode potential, D1 is in, until to that point D1 is in reverse bias. If the D1 is in reverse bias, it acts as open switch. That is, up to crossing this particular Vm, whenever it is greater than V1, then this diode becomes forward biased. Before that, the diode is in open circuited. If it is reverse biased or if it is reverse biased means it acts as a open switch. During the same period, what is the functionality of this one? Let us see. During positive half cycle of the input voltage, uh, cathode of the diode is connected to the positive half cycle and anode of the diode is connected to the negative half cycle. If it is, sorry, negative bias voltage, anode is lesser potential as compared to the positive voltage which is coming from this particular input voltage waveform. So that's the reason until to cross uh, V2, whenever the input voltage of this sinusoidal voltage greater than this V2 voltage, then this particular greater than in the sense, here we have given already the negative. Negative in the sense, suppose this is minus 5 volts. Okay, 5 volts. 5 volts means it's a negative here. If it is anode is negative and cathode is positive means definitely the diode is in reverse bias. If it is in reverse bias means it acts as open switch. If it is open switch and this one is also open switch, in what way we have an output? Let us see that. In the first case, here if it is open and this is, here we are observing if both are open what happens, and whenever the input voltage is greater than this V1, if input voltage V in is greater than this V1, D1 becomes, that is diode D1 becomes forward biased because anode of this particular diode is in higher potential compared to the cathode. That's the reason D1 becomes forward biased. If it is forward biased means it acts as a closed switch. If it is in acts as a closed switch means this is an actually the circuit and it acts as a open switch because until to reach this point this diode is in reverse bias only. That's why it acts as a still as open switch. Okay, if it is open switch in the sense, this is the circuit diagram. Then in what way we have an output? This is a closed switch. V1 appears as its output. That is, this constant voltage maintains at its output. After crossing this particular period, V1 is maintaining constant. Okay. Next, when coming to the next is, okay, whenever V in input voltage is lies in between V1 to V2. This is V in voltage lies in between V1 to V2. V2 is a negative terminals like minus 5 volts to plus 5 volts. Suppose if you consider, if the input is lies in between V2 to V1 like minus 5 volts to 5 volts, then in what way we have functionality? Both the diodes are in reverse passed. If both the diodes are in reverse passed, again the same input appears as its output. That's why this yellow line indicates output is followed by input. During this particular period, both the diodes are in open circuit. You should remember, based on the potentials of anode as well as the cathode, the diode will become a forward biased. If it is in forward biased, it acts as a closed switch. If it is in reverse biased, it acts as a open switch. Into this space. So if both the diodes, that means whenever the input is crossing, like if the both the diodes are in reverse bias, that is actually output voltage followed by input waveform. That is this one. Okay, coming to this, whenever input voltage is an actually lesser than this V2. Suppose this is the V2. Whenever the input voltage is lesser than this V2, that is V in is lesser than minus V2, then this particular diode becomes forward biased. D2 becomes forward biased because the cathode of the diode is, potential of the cathode of diode D2 is lesser than anode potential of the diode D2. Then this diode D2 becomes forward biased. If it is in forward biased, it acts as a closed switch. So this is an actually equivalent circuit whenever the input is lesser than minus V2 voltage. So during this particular period, because of this closed circuit, output voltage is actually V2 only, it maintains constant. After crossing this particular level of input waveform, then these two diodes, actually this diode becomes reverse passed. If second diode also becomes reverse passed. If both are in reverse passed, then in output followed by input. So in this case, this is the waveform you'll have. Okay, output followed by input. Now we can observe in this total circuit, by applying of a sinusoidal waveform as what we have an output. This is an actually output. Okay, this is an actually output we have compared to actually the input. This one is dotted portion is an input waveform and this portion is an output waveform. So based on these biasing conditions, we can observe the functionality of the diode. Based on the functionality of the diode, we can observe output of the waveform. Is it a replica of its input or the biasing voltage, a constant biasing voltage? If it is closed circuit, then that means closed circuit means if it is in forward biased, output voltage is the same as V1, biasing voltage. If it is open circuited, output voltage is the same as input waveform, input voltage. In such a way, we can observe these particular output waveforms. I hope it's a clear. That is clipper circuit with the biasing voltages. The two different biasing voltages by parallel connection of two different diodes here I explained. Okay, coming to the next one. With the Zener diode, how we have evaluate the same functionality of the clipper circuit. This is an actually the Zener diode. So might be before coming to this particular clippers and clampers, would like to complete that Zener diode and its characteristics and behavior of Zener diode in its forward bias and reverse bias. Similarly, if you observe, here D2, D1, two Zener diodes are connected as a back to back. That means anode of the D1, D2 is connected to the series limiting resistor, and anode of the another resistor, another diode is connected to the negative supply of the sinusoidal voltage. That is, here each Zener diode have its cut-in voltages or Zener voltages. We can say it's having V1 and V2s. So if the, because of its connection, D1 diode have its negative Zener voltage and V2 D2 diode having it's a positive Zener breakdown voltage. That is Zener breakdown voltage of V2 is and actually because of its actually Zener diode acts as a voltage regulator in its reverse bias only. In its reverse bias means whenever it is in reverse bias, then it maintains the constant output voltage. If it is in forward biased, it acts as more or less same as PN junction diode. So whenever the V2 is in reverse bias means if it is in negative, it acts as voltage regulator, and whenever V1 is in reverse bias, it acts as a voltage regulator. That's why V1, whenever anode of this diode D1 is negative, it acts actually voltage regulator. That's the reason here given V1 voltage and this V2 as minus V2. So because of this particular condition, whenever the diode D1 is in reverse bias, whenever the diode is in reverse bias, it maintains actually constant output voltage of V1. When the diode D2 is in reverse bias, it maintains the constant output voltage of V2. That is minus V2 and this one is plus V2. So whenever these two diodes are in open condition, then output of this output waveform it's followed by input waveform. During this particular period, okay, output is an exact replica of its input. Okay, this is an actually similar to the last circuit diagram of two PN junction diodes connected in parallel with its biasing voltages of opposite polarities. Okay, now see the series clipper circuits. Till now we discussed the parallel clipper circuits by keeping uh, diodes in parallel with its load resistors. Okay, now coming to the series clipper circuit. This one is diode is in series with the load. Then this is series clipper circuit. Input waveform is same as the last parallel clipper circuits. Now we can observe in what way we have actually the output waveform for this series clipper circuit. Whenever the input voltage anode potential is greater than the cathode potential, the diode becomes forward biased. If the diode becomes forward biased, it acts as closed switch. If it acts as a closed switch, then whatever the here input we are giving will get an as an output. Okay, so that is same as this output waveform. This particular white line indicates the output waveform of its series clipper circuit. If it is actually the diode, if it is in ideal case, this is an actual output waveform. Okay, coming to the practical case of diode, if you have connected such a diode which is in series with its load resistor of RL, each resistor have its internal resistance. So whenever the input voltage is crossing that internal resistance, then it actually acts as a closed switch. So during that particular crossing of input voltage, whenever the input voltage is greater than actually cut-in voltage of this diode, until to that period diode becomes reverse biased. If the diode becomes reverse biased, output voltage is 0. When the input diode of this diode is greater than the cathode of the diode, that is whenever the input voltage of the diode is crosses its cut-in voltage of its diode, then diode becomes forward biased, then output voltage is the same as input voltage. That is, in this way we have input waveform, output waveform compared to its input waveform. After crossing this period of positive half cycle, again at this particular moment, output of input to this anode is lesser than the cathode in the sense here uh, anode voltage, anode potential is lesser than the cathode potential, or based on its an actually cut-in voltage, if it is lesser than actually the cut-in voltage, diode becomes open circuited. If the diode becomes open circuited in the sense, then its output voltage is 0. So the reason here, from here it's having output voltage as 0. This is an actually the functionality of series clipper, a simple circuit. So this is an actually a series clipper circuit, but in this output maximum voltage, how much you'll get? Vm is the maximum voltage in ideal cases of the diode. In the practical cases of the diode, in what way we have, that is Vm minus 0.7 volts. Vm minus 0.7 volts. That is the drop across the diode, if you have considered 0.7 volts, output of this load, that is the drop across the RL, is according to the KVL, Kirchhoff voltage law. So this is Vin. So Vin is equals to drop across the diode plus drop across the load resistor of RL. Now we are observing the load resistor drop. So that is VRL, our output voltage, is equals to Vin minus of drop across the diode. So which satisfies the Kirchhoff voltage law, that sum of voltages in a closed loop is equals to 0. Based on that, output voltage Vm minus zero point 0.7 appears as a maximum voltage and in its output waveform of this, that is Vm minus zero point 0.7 volts. To the next, series clipper circuit with the changing of orientation of the diode. Negative cathode is connected to the actual supply of input voltage source. Anode, in this way, if you have connected to the load resistor of RL, in what way the functionality of the diode. Now let us see. Input, whenever cathode is a higher potential compared to the anode, means definitely the diode is in reverse bias. If the diode is in reverse bias, there is no chance to have any current flow here. That is, it's open circuited. If it is open circuited, means the drop across the diode is 0. That is, current flowing through the load resistor is 0. So drop across the load resistor is also 0, because according to the Ohm's law, V is equals to IR. If I is equals to 0 here, then drop across the load resistor is also 0. That's why output voltage is 0 here with the yellow line here. It's a 0. Coming to the negative half cycle. Whenever negative half cycle starts, that is, cathode of the diode is lower potential compared to the anode of the diode, as like this. So whenever the cathode potential is lesser than the anode potential, diode becomes forward biased. If the diode becomes forward biased, it allows current to pass through it. Then output across this RL is same as input voltage. That's why we have like this. This is an actually output waveform. Okay, in this way just we have a series clipper circuits. Now series clipper circuit with biasing voltage. Already we observed parallel clipper circuits with the biasing. Now series clipper circuit with the biasing. Let us see here. Wherever we have connected the diode, in series with the diode only we are connecting the biasing voltage. Similarly, in series clipper also we are connecting biasing voltage in series with this diode. Now, negative of this biasing voltage source, negative terminal is connected to the anode of the diode and positive terminal is connected to the input voltage source. So in this, whenever the positive voltage of input waveform, sinusoidal waveform, is actually increasing from 0 to the V, okay, 0 to the V. So what happened, actually this negative anode of the diode is connected to the negative polarity of this one. Okay, so until to reach to this particular voltage V, input voltage, until to reach this particular voltage of V, diode is in reverse bias. If the diode is in reverse bias, means this there is no chance to allow current to pass through it. Output voltage maintains 0. Of course here it is an actually 0. Then after crossing this point, whenever the input voltage is greater, I mean anode voltage is greater than the cathode voltage, then the diode becomes forward biased. If it is in forward bias, it acts as a closed switch. If it is acts as a closed switch, then this is an actually closed switch. It output voltage is a replica of its input. Like this we have input voltage. This is an output voltage of compared to the input. Okay, after crossing this point again, this whenever the input voltage Vin crosses this particular point, then automatically what happened, anode voltage is lesser than the cathode voltage. The diode becomes reverse biased. In this case, in what way we can output, let us see here. Okay, this is an actually Vm, output voltage is Vm minus V. This is output waveform we are showing. Actually output waveform is maximum of peak Vm, but because of this particular operation, first it maintains 0 output voltage whenever the diode is in reverse bias. After crossing this input voltage, after crossing this V volts of biasing voltage, then the diode becomes forward biased. During that period, this same output waveform repeats, but the peak voltage is Vm minus V. Input voltage is Vm minus V is the maximum peak appears at its output. That's the reason here mentioning Vm minus V is a peak voltage of output waveform. After crossing the input voltage lesser than this voltage, input sinusoidal voltage is lesser than this biasing voltage, diode again becomes reverse biased. If the diode becomes reverse biased, then no chance to flow the current through this particular circuit diagram. Then output voltage is again 0. Okay, so this is an example we can observe here. For the given circuit, assume that Zener diode is ideal with a breakdown voltage of 5 volts. Find the output waveform across the resistor R. This type of examples I would like to give as online examples, but here I am explaining how we are going to solve this type of problems. Let us see here the input voltage of sinusoidal just denoted as 10 sine omega t. Okay, 10 sine of omega t. This is the magnitude of the signal 10 volts. Okay, and 5 volts is the Zener cut-in volt, Zener breakdown voltage of 5 volts given, Zener diode breakdown voltage 5 volts. And output across this R we are going to measure. So for the given circuit, assume that Zener diode is an ideal. That means if it is in forward biased, we'll consider just the drop across the diode is 0. If it is in reverse biased, we'll consider the drop across the diode is 5 volts. That's the meaning of Zener diode is ideal with its breakdown voltage of 5 volts. Find the output waveform across the resistor R. So if the diode is in reverse bias only, the breakdown voltage is 5 volts. If it is in reverse bias means this is the negative terminal, this one is the positive terminal. By keeping that in mind, just can you draw the output waveform? Just you can imagine and try to form. So this is an actually input waveform, and because whenever you have applied that particular input waveform of 10 volts, because given 10, so 10 volt is as Vm sine omega t is the notation for the input waveform. So whenever the input waveform raising from 0 to 10 volts, here this one is a reverse bias voltage at 5 volts. This is negative terminal and this one is the positive terminal. After crossing that voltage level, before until to reach this 5 volts, diode is in reverse bias. That is Vin is less than 5 volts means this particular diode acts as open circuited during its reverse bias. It's a open circuited means whenever the Vin is less than 5 volts, it's a reverse bias, it's a open circuited. If it is open circuited, no chance to have any current to flow through this. If no chance to have any current to flow through this means whatever the voltage drop here that appears across its output. That is, it maintains actually here the 5 volts. That is, Vin is less than 5 volts. This is actually the circuit operation. Go for, suppose Vin is crosses actually this 5 volts, then what happen? If Vn is crosses 5 volts means like this, just if Vn is greater than 5 volts. If Vn is greater than 5 volts, at the time this particular diode is in forward biased. It acts as a simple diode, that is closed switch. If the diode is in forward biased, it acts as a closed switch. If it is a closed switch means it's a followed by output is followed by input. That's the reason here the same type of output waveform repeated, but its a peak is maximum of 5 volts. So Vin minus V, that is Vin minus 5 volts. Maximum 5 volts, why you are getting? Input is 10 and here we have a voltage source of 5 volts. That's the reason 10 minus 5 means here the output voltage is 5 volts maximum. This is actually the peak of output voltage waveform. In this way, output voltage waveform. Vn is less than 0 volts. In what way we have? It's an appears to be closed circuit. Then input is same as output. Output is same as input. So finally, in this particular example of Zener diode is connected as a voltage source here. That is in its reverse bias, it acts as a Zener breakdown voltage of 5 volts. So in this case, until to have this diode is in forward biased, this particular drop across this diode is, if it is in reverse bias means output voltage is 0. In this way 0. and then it's a forward bias means similar input voltage. After crossing this particular voltage level of input, then again the diode becomes open circuited. Then this diode actually output voltage is same as, sorry, forward biased, then output voltage is same as input voltage. So this yellow line indicates output waveform and that white line indicates input waveform. This is an actually example of analysis of waveforms according to the biasing voltages with the Zener diodes. Now this is an example too with a different waveform of a triangular waveform instead of sinusoidal waveform. For the given circuit, assume that the diode is ideal. Find the output waveform of the circuit. Just how to understand based on the different shapes of the input waveforms, how you are going to generate the different wave shapes with this particular diode operation as a clippers. Okay, and now let us observe this input waveform. 12 maximum of minus 12 to plus 12 as a peak to peak voltage is given, and series limiting resistor or, and the diode is connected here with a positive bias voltage of 5 volts to its anode, and the cathode is connected to the input voltage source. In this case, whenever the input is raising in this triangular waveform, anode is connected to the 5 volts. Whenever the input is less than 5 volts, in its raising condition, whenever the input is less than 5 volts, diode is in forward biased because cathode of the diode is connected to input voltage source. Anode of the diode is connected to the biasing voltage of 5 volts. So initially the diode is in forward biased because the cathode is connected to its input where the input is less than 5 volts. Diode is in forward biased. If the diode is in forward biased, actually this 5 volts only appears at its output. That means just let us, it is in forward biased, in what way we have this 5 volts appears at its output if it is in forward biased. Forward biased means it acts as a closed switch. Then closed switch means the drop across, I mean in between these two terminals the voltage is 5 volts. So this yellow line indicates 5 volts is the drop across the diode across this particular output terminals. Whenever the input is greater, that means greater than the 5 volts, if the input is greater than the 5 volts, so here this is an actually, if the input is greater than 5 volts, the diode becomes open circuited. If the diode becomes open circuited, in what way we have an output? If the diode is open circuited here, the output is same as its input. Okay, this yellow line indicates output waveform. Whenever the diode is open circuited, output is same as input. Then whenever the input is crossing this 5 volts in its falling end, then automatically the diode becomes again, anode voltage is greater than the cathode voltage. At the time the diode becomes again forward biased. If the diode becomes forward biased, output voltage is, if it is forward biased, then output voltage again maintains 5 volts. See here in what way we have output waveform. See, this is an actually initial condition until to cross the input voltage of 5 volts. After crossing the input voltage, then output voltage is followed by input. That's why you have this type of peak as same as a triangular waveform. After in the whenever the input voltage is falling down less than 5 volts, then again the diode becomes reverse biased. If the diode becomes reverse biased, actually the output voltage is maintaining same 5 volts here. This is an actual output voltage. Okay, this is an output waveform and this is an input waveform for this particular diode action. So these are all the things we are going to understand with the analysis of different biasings connected to the diodes either in series or in parallel clippers. So you can take the different examples with the verifying of different textbooks and understand and analyze the different waveforms. Then you come to know that conclusion and you haven't any doubts further with this particular examples of clipper circuits. I hope you are in a position to understand what's meant by the clipper and what are the basic biasing circuits of clippers. What are the different types of clipper circuits we are having? Series and parallel clippers. Series clippers with the positive and negative biasings, and parallel clippers with positive and negative biasing, and dual clipping also we completed in this today's class. Thank you.